It's a pleasure to be here and deliver this lecture. So today I will give a brief introduction to particle methods in specific projection-based particle methods, and also one of the applications of these new generation particle methods will be hydroelastic FSI simulations. So the next and the second part of my talk will be about, in fact, hydroelastic FSI simulations. So the first part is the fundamental aspects of particle methods. So we start from the very famous Cauchy's equation in continuum mechanics, and by having some assumptions, because this equation needs some constitutive equations for both structural mechanics and also for fluid mechanics. And for fluid mechanics, in fact, we can make some assumptions and then we can derive the so-called Navier-Stokes equation, which is the, in fact, conservation of linear momentum here, written in a partial differential form. And also we have the mass conservation for an incompressible fluid flow. So we have these PDEs as the governing equation for incompressible, viscous, unsteady. And in this case, we have Newtonian fluid. And we can also consider non-Newtonian, but in this case, we have Newtonian. And the question is how we can solve the governing equations. So traditionally, we can apply grid-based methods such as, for example, finite volume method to solve these equations numerically. But there are some new generation computational methods, so that we refer to them as particle methods, in which we use calculation points such as nodes or particles without use of any grid. And today we're going to talk about these new generation particle methods, in which we have Lagrangian viewpoints, so we refer to them as Lagrangian Meshfree methods. So if, in brief, I would like to introduce particle methods, we would just say, okay, they are Lagrangian Meshfree methods. And the key idea here is that we would like to have a stable and accurate solutions for our PDEs, or for our partial differential equations, for which we have specific boundary conditions, initial conditions, and we would like to solve those equations using these numerical tools, numerical techniques. And in today's presentation, I will briefly introduce two particle methods, namely SPH, which is a smooth particle hydrodynamics, and also MPS, or moving particle semi-implicit method. SPH is a microscopic and deterministic, in fact, particle method. It was proposed in 1977 for astrophysical applications, and the solution process is fully explicit. At the heart of SPH, we have a simple weighted, in fact, averaging, in fact, interpolation scheme, and this is the heart of SPH. So if you would like to obtain some values, some physical values at some target particles, what we do is just calculate, in fact, a weighted average, a local weighted averaging of the values at the neighbors. So this will give us some values at the target particles. And if we have a fully explicit solution process, such as the original SPH, so this is like what we have as conventional SPH methods. But at the same time, so we have also several other particle methods. And today's talk will be focused on projection-based particle methods. One of them is related, in fact, to MPS method. And for MPS, in fact, it was proposed in 1996 for incompressible free surface fluid flows by Professor Koshizuka at the University of Tokyo. And the solution process is semi-implicit. The SPH version of MPS is called ISPH, or incompressible SPH. And these two projection-based particle methods are founded on a rigorous mathematical context, which is Helmholtz-Larrey decomposition. And this is the difference of MPS and ISPH with respect to the conventional SPH, because in conventional SPH, for example, the hydrodynamic pressure is found by using an equation of state, a thermodynamic equation of state. But in case of ISPH and MPS, we have the Helmholtz-Larrey decomposition. And this decomposition is a very simple one. So if you have an arbitrary vector, which is our intermediate velocity field here, which is the predicted velocity. So it can be decomposed into a divergence-free one, which is the solution that we would like to have, because we have incompressible fluid flows. For incompressible fluid flows, we need to have a divergence-free field based on the continuity equation. And at the same time, so decomposing to a divergence-free one and a curl-free which is the gradient of a scalar field. And I'm sorry. So with respect to the original particle methods, in fact, we will have an enhanced pressure field and enhanced volume conservation. And this is the advantage of the projection particle methods. So I will have a brief look at the Helmholtz-Array decomposition. So if you would like to have more detailed explanations, there is an excellent textbook, which is the Navier-Stokes and Turbulence. We can have a look at this, in fact, textbook. But briefly speaking, so when we have Helmholtz-Array decomposition, we have an arbitrary vector field decomposed into a curl-free here, which is the irrotational one, corresponding to the gradient of scalar, because curl of the gradient of scalar is 0. And also we have a divergence one, and we can prove the orthogonality and also based on some conditions, which is written here, connectivity condition and having specific, in fact, boundary conditions using divergence theorem. We can, the key point is that we can prove the uniqueness and exactness of solution if we use this kind of technique, this kind of projection, in fact, technique, which is the Helmholtz-Array decomposition. And in brief, what we have, in fact, is this decomposition for projection particle methods. So we have divergence of velocity 0 in the domain. We have, in fact, V dot n no slip boundary condition, for instance, for the boundaries. So we do not have any mass flux at the boundaries. So this is rational. And also we have connectivity conditions. So this is also important. So these three conditions together with Helmholtz-Array decomposition, we can have exact and unique solutions for the governing equations, which is the incompressibility condition, so continuity equation. And also we have the Navier-Stokes equation in a simple form, excluding turbulence. And applying this, in fact, for projection-based particle methods, what we can have is just a Poisson pressure equation. So we solve a Poisson pressure equation in projection-based particle methods, in contrast to the conventional SPH, in which we solve an equation of state. So in this case, we need to solve a global, in fact, Poisson pressure equation. This has advantages. So the advantage is that you can have more accurate pressure field, conservation quantities will be better guaranteed. But the point is that you will need to have more, in fact, computational effort to solve a global matrix, in fact. And we can have different differential operator models, such as, for example, the one that I show here for original moving particle semi-implicit method, or we can have a revisit of the derivation to, in fact, derive these schemes more carefully, and that will be the refined particle methods. And so one question for us is that, okay, you have, for instance, conventional grid-based methods. So why using particle methods? So the answer to this question is that if we have specific problems, for example, problems that are characterized by large deformations, or problems in which we have complex geometries, complex physics, moving interfaces, so these new generation computational methods will provide us with a potential for, in fact, simulation. So this potential is highlighted here because we need to be very careful about derivations, about consistency of mathematics and physics. And this will lead to the refined particle methods. But for the past, in fact, we had so many issues with particle methods. And this is like some original simulations, some simulations by the original MPS method. So we had several issues related to the non-exact momentum conservation incompleteness, on physical pressure noise, unreliable convergence properties, computational time, which was quite huge, and also inconsistent boundary conditions. But during the past years, we have tried to solve the issue. And we can see here, in fact, some of the results by original MPS and ISPH, and these issues have been solved. So these results correspond to 2008. But these results have been solved, in fact, by applying the refined schemes. Or this one is a paper published in 2007. We can see spurious pressure noise here. Even after averaging, we have 50% underestimation of the peak pressure in an ocean engineering application. But these days, in fact, we have refined particle methods. We have, in fact, accurate particle methods for which we can have more reliable solutions based on the refined schemes or refined algorithms. So during the past, again, decade, we have developed several schemes here. Some schemes, for example, for enhancing the momentum conservation or ensuring momentum conservation in many cases. And also we had some schemes for improving the accuracy, some schemes for improving conservation, including energy conservation or volume conservation, some schemes for improving the, in fact, imposition of the boundary conditions in free surface fluid flows, for instance, and some schemes to improve, in fact, consistency and, in fact, stability, because, in fact, regularity is an important issue for particle methods. So we implemented optimized particle shifting. And so due to the lack of time, in fact, I will just have a brief look at some of the improvements. So I'm not going to show the schemes because all of them are available in our journal papers. But one of them, for example, in 2011, so this is available in Journal of Computational Physics. So we can see this is like MPS with only 2 improvements. So we could not reproduce high velocity impact, jet impact here. But when we had 4 improvements, including, in fact, some corrections for the gradient operator and some corrections to improve the volume conservation, or in other words, minimize projection errors. So we could reproduce such, in fact, important problems accurately. And also violent sloshing flows, which is very common to be solved in ocean engineering. This was another problem that we were looking at. And in fact, we had some schemes like the DS scheme to enhance, to minimize, in fact, the effects of any artificial stabilization. So we could just find some accurate scheme to ensure the stability for particle methods, and also some schemes to improve, in fact, boundary conditions. So if we have like truncated boundaries and lack of, in fact, compact support, we could use space potential particle to, in fact, improve this aspect. The other scheme that I would like to introduce is simply a shifting technique, a particle shifting technology, or PST technology. And this is based on, in fact, fixed diffusion law. And the important point is that we have Lagrangian methods, Meshfree methods. So in some cases, so particles will just become anisotropic. So we need to make sure that we will have, in fact, isotropic particle distribution. And in this case, so we had PS scheme. We had very good results, in fact, for internal flows. But in case of free surface flows, we had to be more careful. And this is one of the schemes that we developed in 2017, published in JCP, or Journal of Computational Physics. So the key point is that this scheme needs to be, in fact, parameter free. So there is no need for doing any tuning. And also we need to eliminate shifting normal to the interface, and it has to be physically consistent. So if you have regularity in particle methods, that will be very helpful for consistency, conservation, and convergence. So we had some test cases to, in fact, validate the scheme. And this was the first part of the talk. So we, in fact, I just briefly introduced some of the refined schemes that we had for improved simulation of free surface fluid flows or multi-phase flows. But in this section, I'm going to talk about the hydroelasticity and reproduction of hydroelastic fluid structure interactions by using, in fact, particle methods. So in ocean engineering and in fact, marine engineering, one of the problems that we're facing is interaction of violent free surface fluid flows with structures. And in many cases, we need to also consider elasticity or elastoplasticity of the structure. So in such a case, we need to develop advanced computational methods for this purpose. And so for particle methods, in fact, one of the questions is that, okay, why we should use particle methods, why we should use, in fact, a fully Lagrangian Meshfree hydroelastic FSI solver. So this means that for both fluid and structure, we're going to use mesh-free particle methods, and then we are going to couple these two for hydroelastic FSI. So to answer this question, in fact, we can just mention we face violent flows in ocean engineering, And also at the same time, we need to be very careful about interface boundary conditions. So if we have the same classes of methods, the same methods, I mean, from the same class, which is the Lagrangian Meshfree, it's going to be easier to rigorously satisfy and guarantee the satisfaction of interface boundary conditions. And then we have, in fact, adaptivity or applicability, which can be also easily extended when we would like to use, in fact, different resolutions for fluid, different computational resolutions for fluid and structure. But this is the first question. Okay, we can use particle methods, but why using projection-based particle method? This is because, in fact, not only because of accurate pressure field or volume conservation, but also because if we use, in fact, projection-based particle methods for the fluid phase, then we can have a very robust algorithm to ensure a consistent coupling as one of the important features that we need to pay attention to. So we use, in fact, our refined MPS or ISPH method, our refined projection-based particle method for the fluid. And then we will use, in fact, some development for some developed structural models. And in this case, for the fluid, we have a continuity equation. And for, in fact, linear momentum conservation equation, Navier-Stokes equation. And these equations need to be solved. And at the same time, for structure, we have, if we are focusing on Newtonian mechanics, we will have notion of force, conservation of linear momentum, conservation of angular momentum. They're written here in continuous form. We need to discretize them using differential operator models in particle methods. And then the important point here is that how we couple a two-way coupling, consistent coupling of fluid and structure. So in case of Newtonian mechanics, in fact, we have developed some methods, and also we can have another approach that I will mention later about the Hamiltonian mechanics. And so there are four aspects for, in fact, development of hydroelastic FSI solvers in the context of projection particle methods. And one of them is related to the choice of governing equations. And that depends on your interest, because if you are like very sensitive about the energy conservation or very precise conservation of momentum, linear momentum, so in fact, you need to consider, okay, it's better to use variational approaches, for instance, looking at the Lagrangian or the Hamiltonian mechanics. And then we have, this is like related to the choice of governing equations. So in brief, you can consider Newtonian mechanics or Hamiltonian mechanics. And for, in fact, interface boundary conditions, we need to ensure that in discrete form, these boundary conditions will be guaranteed. And then adaptivity or applicability also needs to be ensured. And then generality, because we may have, in fact, not only elastoplasticity, but also we may have, for example, composite structures, or, for example, orthotropic structures, so in which we do not have isotropic behavior in matter. So we need to consider all of these aspects for development of a robust, reliable, hydroelastic FSI solver. So in terms of Newtonian formulations, so in fact, we consider linear and angular momentum conservations. The notion of force is considered. For Hamiltonian mechanics, in fact, we will solve just one simple equation in which acceleration is a function of variation of a strain energy density function. And so if we have, in fact, if you would like to have more flexibility or even extensions, for example, to consideration of physical damping in a structure, because we can just consider simply the, in fact, laws related to the thermoelasticity, and then we can have, in fact, very robust, very accurate solvers being developed in the context of Hamiltonian mechanics. But one of the issues is that it's numerically more challenging, so you need to devise more schemes or more careful schemes to ensure stability without adversely affecting the conservation features or the accuracy. So this is the first point about the choice of governing equations. So we can consider either Newtonian mechanics, and this is the Hamiltonian conservation of linear momentum, which is derived from, in fact, Hamilton's principle of least action. And here, in fact, as we can see, acceleration is a function of the variation of psi here, and psi is the strain energy density function. So the advantage of this approach is that if, for example, we would like to treat different materials, what we can do is just changing psi for different materials that we are dealing with, and then we can just solve the equation based on the constitutive equation that we have. So if we would like to compare Hamiltonian, for example, SPH with the SPH, so basically in many cases the results will not be that different, because if we develop the schemes consistently, so in that case we will have accurate and stable solutions. But one of the important aspects for Hamiltonian mechanics, Hamiltonian structure solvers, is that we can guarantee preservation of energy if, for example, we do not have any dissipative forces, so energy must be conserved, and this will be the case. And this is, for example, one classical benchmark test. We have a sudden, in fact, loading of an aluminum plate by water. So at the beginning, so the aluminum plate will be subjected to some sudden external loading, and then the FSI system needs to reach an thermodynamic equilibrium. So when we use, for example, refined schemes together with Hamiltonian SPH or even Newtonian SPH, we can see we have a straight line here close to the theoretical solution for the deflection of this point. And this shows that, okay, we have almost reached the thermodynamic equilibrium, which is in fact very difficult to attain this numerically. And the total loss of the energy is just 0.2% for 1 second of simulation. So this is the advantage of using, in fact, refined schemes and doing a very careful development for hydroelastic FSI. So the other approach, the other fact that we need to discuss is related to the fluid structure interface boundary conditions. Due to the limitation of the time, I will be very quick about this as well. So what we need to consider is that we need to ensure that the interface boundary conditions, which is written here, for example, normal stress continuity, needs to be precisely guaranteed. And this needs a very careful, in fact, derivation of the schemes. And this is published in Computer Physics Communications 2018. So interested audience can refer to this paper for more information about the development of hydroelastic FSI in the context of SPH. And so for the third part, which is related to the adaptivity, so this is also another important point, because adaptivity is known to be one of the grand challenges of SPH. So because we have Lagrangian Meshfree methods, and then we would like to use different computational resolution for fluid and structure, or in different parts of fluid. For example, we would like to refine the resolution at some specific locations because we would like to have more accuracy in those locations. So this is very important. And we need to develop these schemes without adversely affecting the accuracy, the consistency, the conservation of the overall method. So this is also very important. And for this case, in fact, we need also to pay attention to, for example, for hydroelastic FSI, to the continuity of normal stresses at the interface. And this is published in Applied Ocean Research in 2019 related to a hydroelastic NPS-based solver. And some results are shown here. So we can see a sloshing flow, and this violent sloshing, in fact, is reproduced by some particle-based methods, and you can see we have different resolutions for fluid with respect to the structure. So in these two cases, so the resolution is, so the diameter of the particle for structure and fluid is different. So 2 and 2.5 is a DF to DS ratio here. And this is for the case that we have the same. So all the results show almost the same deflection time history, almost the same. This is the deflection time history, and the previous slide showed almost the same, in fact, spatial distribution of hydrodynamic pressure and the stress in the structure. And the last part of my talk will be related to the generality for the development of the solvers. And firstly, we need to make sure that we can easily extend the method to 3D, which is the case here. And also the choice of constitutive equations for different problems that we are solving. We need to be careful to properly select the proper constitutive equation. And this is very important because if we are in the Newtonian mechanics, so we need to properly set a proper constitutive equation, but then we need to take divergence of the stress tensor, and this may need some careful, in fact, attentions. And at the same time, we have composite structures and composite materials to be considered. And for all these test cases, we need to firstly do a rigorous validation, not only by referring to the experiments, but also looking at some classical structural mechanics or fluid mechanics, continuum mechanics problems. For structure, for example, here we have an oscillating plate. So on the basis of Kirchhoff's law of plate theory, we can have exact solution, we can have a theoretical solution. Then we can look at the, for example, kinetic energy variation in time or the normalized energy. So we can see for the Newtonian particle method, we have some oscillation in the energy, but for Hamiltonian one, it's a perfectly straight line. And some other test cases related to the ocean engineering, which is reproduced here. And finally, I'm going to just give some concluding remarks here because of time. So the point that I highlighted in the second part of my presentation was related, in fact, to several aspects, for example, related to the generality, related to the interface boundary conditions, related to the adaptivity, and also related to the appropriate choice of governing equations. So based on our, in fact, vision, we can properly select the governing equations, but these, so we are continuing these studies for, in fact, multi-phase, multi-physics, and multi-scale particle-based simulations. And I would like to thank you for your kind attention. Thank you.